Okay, so while we get the speaker set up, I'm happy to introduce the last speaker of the session. Chang is a PhD candidate at Caltech in experimental particle physics. Besides his physics analysis of projects, he works in the development of methodologies and toolchains for the efficient deployment of real-time machine learning models on FPGAs for the CMS experiment. You may recognize him from the previous years. He previously gave a talk in the DA for ML, and this year, Chang will be giving a talk on high granularity quantization for real-time neural networks and lookup table-based inference. Okay, welcome, Chang. If you're ready, feel free to start.
Oh, can you hear me?
Yes, you can.
Big one. How do I point?
Okay, this one. Yep.
Okay. Okay, relative motion. Okay, I will talk about high granularity quantization for basically deploying neural networks from FPGA for fast inference, mainly for the level 1 triggers. But hopefully we can find some other applications, I don't know. The code is here. If you are interested, you can scan the code, and it's also a hyperlink you can click if you download the PDF. So some background I will go through very fast here. We are a bit late, I think. And it's basically the level 1 trigger outline of the CMS experiment. We have around 500 FPGAs here, and we need deterministic latency under 1 microsecond for one individual subsystem. It's usually around 2 clock cycles or even 1, from 25 nanoseconds to all the way around near 1 microsecond. And we need a deterministic latency. This means we want to deploy the neural network on FPGA fully or mostly on road, meaning each of the individual affine operation is mostly done in parallel. Meaning real factor in HGQ-LUT, if you use that tool, it's 1. You can find concrete examples, but in most cases, that's the case. And the baseline is basically using QKeras with whatever hyperparameter optimization framework on top and through HGQ-LUT. And this is just one example where we have autoencoder deploy a CMS experiment at this moment, which is VCRAC representation learning and variation autoencoder through the reconstruction loss. There are 1, 2, 3, 4, 5, 6 layers here with some other aggregation operations, all done in 2 clock cycles. So here we don't really have the systolic array or multi-cycle inference of each individual computational call, but instead we are basically building each of these neural network blocks in a combinational block. So everything in parallel, just a bunch of wires and 1 layer of register in the middle. So since we are unrolling the neural network, we don't really want a uniform bit width through the whole tensor operation. You have a matrix, you multiply by 1 vector, but we don't necessarily have the same bit width on this whole matrix, so we can save some resource. For example, if you have only 1 bit, that's a shift operation, and the MAC operation becomes only a shifted addition. This is actually aligning with the distributed arithmetic work I did last year. If you remember, the motivation was basically that you can decompose the mathematical operations into optimized adder tree, and if you have lower bit widths, there are basically less operations. So here, if you want to assign different bit widths to each different parameters, it becomes a nasty optimization problem. We don't know what bit width to give to which parameter. So here, the solution is that we want to do a differentiable quantization. So the bit widths are optimized by the gradient along with the weights themselves during training instead of we manually set them to some values. And this is just a high-level demonstration. In the non-quantized case, every edge is representing a high bit width weight, and a node is activation bit width. If you do the quantization, the width can be lower, but it's still uniform across layers. And you do pruning, it's still. But if you do the high granularity quantization, you do pruning and quantization as one shot. Because the 0-bit width, the 0-bit quantization is naturally represented as pruning. And this is actually a FPGA 26 work that's presented a few months ago. And the algorithm is as follows. Consider here when we talk about quantization, we consider the fixed point quantization, which is hardware friendly. And we consider the signness, whether it's sign S, the number of integer bits excluding the sign as I, and the number of fractional bits at f. And the quant as of a parameter x with these parameters is the number itself plus the quantization-induced error. If we substitute x during training with this formula, both x and delta here will receive a gradient. So if we know the gradient of delta, del f, number of fractional bits, we can have a gradient on the number of fractional bits. Integer bits here is directly to cover the whole range of the x dynamic range, and sign or not is depending on whether there's a negative or x or not. So here, delta is induced by two parts. One is rounding, one is clamping or overflow. Overflow or clamping is handled separately, but for the number of fractional bits, we assume the foundation-induced error by the number of fractional bits is a uniform distribution from basically minus 1/2 of the RSB to plus 1/2 of the RSB. And the loss is insensitive to the sign of this delta, so we assume the loss is the same if we move left or the right in the quantization error. So basically, we are around the bottom on the loss landscape. So only the second order term effects. And if we do alternative form of the finite difference approximation, you can look at more details in the paper. We see that the absolute value of delta f is approximately this form. And if we do the mean field approximation to average out this highly random value, we got del delta f to the number of fractional bits equal to this value, and we plug this into the training to get a circuit gradient on the number of bits required. And for the overflow part, we can have the saturation or the wraparound. For saturation is simple because clamping has gradient, so we just put it in. For wraparound, we prevent the overflow statistically because that will usually trust the results directly. You can look in more details in the paper. And this one only pushes the bit width to infinity, and we need another term to push it down to 0 or make it resource aware. So here, what we propose is a very simple circuit model for the resource utilization of a dense kernel or the affine operation, plus some other small operations, actually. The idea is very simple. For the MAC operations, if you do a multiply by a number of m bits, or bi, multiply by another number of bj bits, you simply multiply these two number of bits together and sum of them. And for the addition operations, you just take the maximum of the 2 bit widths of the operands, and you sum them up, and you get EBOBs. You multiply these EBOBs by a factor of beta, which is a hyperparameter, into the loss term, and you do the training directly. This EBOB is supposed to predict the model resource utilization directly during training as a differentiable circuit. And with the distributed arithmetic optimization, this comes out very nicely as an approximate exponential term of the actual resource usage. So if you put this thing in, you get almost the resource utilization after place and route directly during training. And we use this as a differentiable circuit of the model resource in the loss term. And the error is between minus 40% to 40%. It's not very nice, but there are some outliers, especially with SVHN, which is using the IO stream architecture, which introduced some overhead in the buffer instantiation and the controlling. For the block of models, the MLP models is usually between 10 to 20%. And this also accounts for the fact that if you change the synthesis strategy, itself would create more than 10% fluctuation, so we consider this circuit to be good enough. And the quantization with distributed R's, and this is just the quantization part. And if we consider the new famous LUT-based arithmetic, we can actually, instead of representing neural network as a mathematical problem, we can represent it as a lookup problems to basically abuse the lookup tables in the FPGAs better for better efficiency. So the quantization with distributed arithmetic is usually having lower the precision of the operands and use shift-add-based operations instead of the real MAC operations. However, with FPGAs, this is basically using the 6 or 5 lookup tables as 3-to-2 or 2-to-2 compressors, or the full and half adders. Even consider the carry 8 primitives or the full adder primitives in Altera or the Xilinx FPGAs, the lookup tables will not be fully utilized. However, with the lookup table-aware approaches, we can make better use of these hardware primitives, or the arithmetic will be aligned better with the FPGA fabric. A generic N-to-M function can be efficiently implemented with the lookup primitives by using the max operations. As long as the number of input bits is less than 9, with Ultra Scale Plus, you have the F789 hardened maxers. And this is demonstrated efficiency in parallel works. And this is based on the FCCM paper we just published 2 weeks ago. And however, the challenges in the current LUT-aware training approaches is that the training is the order of magnitude slower than standard QAT, even if you don't consider the quantization overheads. It's just inefficient because of the memory, either in the dynamic routing or in the function approximation. Also, it's limited to the multi-layer perception directly derived from this inefficiency in training. And also, without efficient quantization way, you have to still manually set the bit widths of each layer or group of lookup tables, which causes more inefficiency. So for the fast lookup table-based training, we first reparameterize the MLP in this form. So basically, we advance the activation operation from the end of the layer to the beginning of the layer. And if you have a launching of MLP, it doesn't matter. And we replace this bunch of operations, so basically activation, and do a find on it. So this is a unary function. It can be implemented as a generic N-to-M function, or N-to-M lookup operation, which can be implemented on FPGA very efficiently. However, we cannot directly train a lookup table on the GPU, which is inefficient. So what we do is we, again, implement this very small lookup operation as a 1 to N to 1 MLP, or 2-layer perceptron. And this relaxation makes the whole layer operation a big Einstein operation with activation in between. So it is GPU friendly. And this indeed achieves around 100% speed up, 100 times speed up compared to pair works, I will show later. And for the resource utilization circuit, because this is no longer EBOBs, we have to add another lookup table circuit. Consider F789 primitives on the Ultra Scale Plus FPGAs already. For anything of greater than 5 bits inputs, we consider the fluctuation limit of the lookup tables is basically n minus 5 to the power of 2 of that, times the number of output bits. If it's less than 5 bits, the compiler is doing something smart that we have no control, but it's mostly linear. So we use a linear approximation down for the one below, which is not that accurate, but OK. And and this one directly enters the EBOBs. There's this exponential relation. The coefficient is very small, so we enter this linear form is mostly OK. And N and M, if one of them goes to 0, again, this lookup table is pruned, so we don't need extra pruning for this still. And the workflow is like this. So we can, first we train the model, and we send this to the FRML of the symbolic tracer, and it goes to IR, lowers to the RTR directly. And here, actually, we get a more accurate form of circuit, which is around 5 to 10% resource utilization if you use the correct strategy, which is error optimized medium in Vivado synthesis. If you use other strategies, the fluctuation will be there based on the strategy itself. And there's fast simulation. There's big exact simulation in the interpretation form or in the variator form, and auto pipelining and retiming, and also the output. So it's end-to-end workable. You can generate an RTL kernel that is deployable in the trigger system directly, either in Verilog or VHDL. And you can also go through the conventional HSFML flow, but the support is more limited now, and the support is actually now secondary. because the DFML can cover most of the use cases, and we are still working on the multi-cycle inference or the data flow inference. But with HGX-FML, the LUT-based arithmetic is not supported, but everything else is mostly still there, and you can still use the DFML optimization. And regarding the training speed up, the pure state-of-the-art training speed is here, number of microseconds per batch, and we are here. For the HGQ lookup table-based inference, training, and without lookup table is even faster. And the bit width is obtained is as expected. If we have a higher accuracy, the bit width is higher. If we have lower accuracy, the bit width is lower. And it's a distribution. And we have a significant amount of 0 bits, so pruning is working as expected. And for both of the weights and activations for different models. This one is a J classifier. This one is a bigger J. This one is a muon tracker or the track regressor. And with this method, we dominate the Pareto front on the conventional jet tagging baseline. These are all the works, and the black ones are HGQ, and the blue ones are HGQ-LUT. We dominate the Pareto front. And we can also combine these two approaches in one network. You can use some part of it to be conventional MATML-based, and some part of it to be the lookup table-based. And again, we achieve the state of the art with the hybrid approach here. And if the pure HGQ approach still outperforms the baseline by a significant margin. And also, this is a particle level jet tagging on the HGX-FML dataset. This is HGQ versus HGQ-LUT. HGQ-LUT is performing better here, but maximum accuracy here is a bit lower because the model we use here is actually of a smaller scale for faster training. But if you compare the HGQ or HGQ-LUT with the pairs baselines, it's orders of magnitude. The thousands of DSPs go to 0, and the lookup tables also goes by a few times. And all of those are MLP or not really MLP, but JDLinear is actually a static graph neural network. And this one is actually COM1D network with multi-cycle inference with some manual Verilog writing, and is achieving an improvement comparing to the classical baseline. There was actually also one convolutional neural network example in the paper on SVHN dataset achieving better results, but I will skip it here. So in conclusion, we propose HGQ, HGQ-LUT, and HGQ. Sorry, I think I forgot to replace the conclusion slide. But basically, we propose the method, and it's working. We have the end-to-end framework and end-to-end integration, and we look forward to applications beyond the particle physics. Thank you.
OK, thanks again, Chang. Questions for Chang? OK, I can maybe ask a quick question regarding the training speed you were comparing with the other frameworks. If I understand correctly, this one specifically, if the output of this you can put directly onto the DFML.
This one is sorry.
Sorry, I'm just asking here. So the output of this guy put directly to the DFML.
Not DFML. The NRA and the Canela here, they have their own in-house RTR generation.
OK, all right.
Yeah. So basically, the NRA is another lookup table-based training, and the Canela is another lookup-based training. So they can only support basically MLP-like lookup table networks. But with DFML, we can combine anything. So anything that is supported, we can combine them together in one design.
OK, very cool. Is this open source already?
Everything open source.
OK, great. Very nice. Any other questions for Chang? OK, go ahead.
Hi, it's Istvan from Silicon. So this is very like LUT-heavy design. Do you have any estimation if you can have a higher Fmax, how that is influencing the performance?
Sorry, I cannot hear a bit.
So I was asking if do you have any estimation if you have higher Fmax, then how is that influencing the performance?
If you are talking about latency and Fmax, latency Actually, after deformer conversion, you get around 20% accuracy estimation. But that also depends on your pipelining and other things. For Fmax, it's really down to the pipelining part. Like how many registers do you want to insert in the middle? And that directly translates to what Fmax can you actually achieve.
Thanks.
Okay, great. Any other questions for Chang? Okay, if not, let's thank the speaker again. Thanks a lot. And this is the end of our session.